Okay, so our first unit is on something called kinematics, and I've used that term a lot. So why don't I actually start by now maybe defining it a bit better for you guys. So kinematics is essentially the study of motion. If something is moving, that's what kinematics studies. So we're going to be working with variables like how far did it move, how fast did it move, was it speeding up as it was moving, can we plot it in a linear direction, does it just go flat, does it go in an XY direction, does it have a little bit of up and downness to it if something goes in the air. Typically, I would say that we either deal with things that are going in a straight line, or we deal with things that have this sort of shape to them. If you're in grade 12, you might recognize that's a parabola. Those are the main things we'll do. In physics, you can actually do things in the X, Y, and Z direction. Let me make sure you understand those terms. X would be a straight line like this. The Y direction would allow for it to go up and like that. So I could point my gun straight that way and shoot. I could put my gun straight up in the air and have a bit of an angle to it. So that would be the X direction. The Y direction. The Z direction means that I could swivel it and kind of aim it anywhere in that direction too. So we don't actually do 3 dimensions, we only do 2 dimensions, which is good because for you guys that were in my grade 11 class yesterday, when we do systems of equations, if you want to do 2 variables, you need 2 equations. If we wanted to get to our 3rd dimension, we just need to have 3 equations, and that gets to be a bit too much. Quick review of just chemistry and physics and some of the words we use. Physics is all about matter and energy. That's kind of the definition of physics in general. Usually this is kind of my introductory notes. Let's just move on. Alright, let's move to this slide here. This is really where I need to start. All those slides there are usually like my first day notes. We don't need them anymore. So here's what we've got so far. Since we've done some review, you guys should know how to do distance and displacement, speed and velocity, acceleration and time. And so our goal today is to basically be able to track the motion of any object in terms of these variables using all sorts of different formulas. And these are known as the kinematics formulas, some of which you guys already know how to use because they're actually great time. So let's walk through what we know about them so far. This formula right here is your basic velocity formula. I gotta make sure I'm very clear about it. It's your average velocity. If your velocity ever changes, if it speeds up or slows down, that formula is not very useful. If you have what's called uniform motion, where you're always going the exact same speed on cruise control, then that formula makes sense. But if your velocity is going to change, that one's not really useful. When we race our Hot Wheels down the track, we won't use that formula because the Hot Wheels will start with a high velocity and they will eventually slow down and stop. If you tried using that formula, you'd find the average velocity. The average velocity would be the speed it was going right at the halfway point as it went down the track. That'd be where the average would be, right? But only for one moment in time would it actually ever be going at average velocity. So, although that's a useful formula, we don't use it nearly as much because of the fact that you have to have consistent speed. This one right here, we can use. It's very rare that our acceleration is not constant, though. Like when the pen drops due to gravity, is gravity sometimes 9.81, and then sometimes 9.73, and then sometimes 10.51? Or is gravity pretty consistent on Earth, right? So unless for some reason your acceleration is changing, then we can use this formula here. So, and this one here, I want to point out something here. This change in v kind of implies something. It implies that you take your final velocity and subtract your initial velocity. So in a sneaky way, there's actually 2 variables that could be in there. It could be your final minus your initial. Often, one of those 2 is 0. Like often, either you're ending up stopped, or often you're starting from a stop. You don't have to, right? Like if I slam on the brakes of my vehicle, I was going 100 kilometers an hour, and now I'm going 20 kilometers an hour. The change in velocity would be negative 80 kilometers an hour. Does that make sense? So the numbers don't have to be a 0 for either one, but it kind of implies that you need to know 2 different velocities for this. The other formulas that we've learned so far are these guys. which essentially are formulas that involve either a final or an initial velocity, a distance, and a time, along with acceleration. So we're going to add two new ones today, this one and this one. And I don't really ever go through how the formulas were developed. If you'd like to, we can look it up. It's calculus, so it's maybe a little bit beyond where we're at yet. But so long as you take my word that these formulas are true, what's unique about them is each of these formulas here more or less covers a scenario. In essence, there's probably 5 variables you could ever be asked for. You could ask for time. That's a scalar. You could be asked for your acceleration. You could be asked for a displacement, and you could know your initial velocity and your final velocity. There's probably 5 main things we ever look for. These formulas cover basically all possibilities of solving for something. If you know a velocity final, a velocity initial, and an acceleration, you can find a distance. If you don't know about time, like let's say you have no information on time, use that formula. If you have no information on acceleration, you could still use this formula. If you have no information on velocity initial, you could use this formula. If you have no information on velocity final, you could still use this formula. And if you have no information on your distance, you could still use this formula. See how that works? It's kind of clever. So of all these 5 variables I gave you there, if there's ever one variable that you don't happen to know anything about, and you're like, it's like you're missing one, you can actually still use the formulas, because all of these formulas involve 4 out of our 5 variables. Let's do a bunch of examples though, because that's really the point of today. So just some teaching questions. There's a train, it's breaking down, it's decelerating at a rate of 4.5 meters per second. As I read through, I'm just going to write out some of my my things that I know. It gave me an acceleration of 4.5 meters per second squared. So this means I need to use a formula that has an a in it somewhere, right? So right off the bat, I know which formula I'm not using. I am not using that one there, right? Because that formula doesn't have acceleration, right? What else is wrong about what I wrote here? Good catch. Yeah, because it's decelerating, right? Okay, time, 20 seconds. Okay, it says that we're going to slow down to a speed of 2 meters per second. That's a velocity final. So velocity final will be 2 meters per second. And it wants to know our distance. So our goal is to find a formula that does not have, what's the variable that we don't have listed on the list here? Yeah, so basically find the formula that does not have velocity initial, which is this one. That makes sense? And then at this point here, it's really just algebra. So the formula we're going to require is that your displacement is equal to velocity final times time. We've used this one before, right? Minus 1/2 at squared. We're looking for distance. Sounds good. Our velocity final will be 2 meters per second times by 20 seconds minus 1/2 of minus 4.5. I'm going to point something out here. That was a negative acceleration, right? But it's kind of cool how the formula works. The double negative means it'll get added. Can you get that? Is that a breakfast card? Nice. You guys are doing a breakfast card? Anybody hungry?
Breakfast card that had like pancakes on it and bacon. Yeah, and like fruit bowls. It was good.
We've got yogurt and oranges.
Probably tomorrow.
Oh, and
Maybe that's just a Friday. Yeah.
Thanks, guys. All right. Where were we? Oh, I was trying to point out the fact that the double negative is going to add, which I think makes sense, right? Because when you're trying to slow down in your vehicle, we're going to need some stop. Like it's going to take you a while for your vehicle to slow down. You know what I mean? Like it doesn't happen on a dime. And so however fast you're going times time, we're still going to actually need to have some more added on just for that stopping distance. So, let's see, meters per second squared, and then 20 seconds squared. Someone help me out. Anyone's got an answer yet?
I got 940.
Anybody else? 940? Cool. The units for that seems like it would be meters, right? Let's just walk through why. This seconds and this seconds right here would give you meters. And this second squared would cancel with that second squared to give you more meters numbers. And then as you combine your meters values together, it would stay in meters. So apparently you need 940 meters for this train to slow down. Oh, good catch. Thank you. With sig digs, let's make it 9.4 times 10 to the 2 meters. Thanks, Jessica. I got that right. Essentially what we're trying to do, right, is you need to be able to do your algebra. You need to be able to do your sig digs, all that stuff. What's really new today is just figuring out which of the 5, 6 formulas you need to use. I think we did one like this before, actually. There's a parachuter. He's 1.53 kilometers above the ground. And he is being decelerated by his parachute at a rate of 6.3 meters per second per second. I want to make sure we're clear on this. He is still going downwards. But his velocity is actually trying to pull him back up. Does that make sense? That's what the parachute essentially does, right? If you've ever been parachuting before, as you free fall, when the parachute comes back down, it kind of starts pulling you back up again, right? As it's slowing you down. It takes 25.7 seconds for him to hit the ground. What was his velocity when he initially opened the parachute? So let's write out some stuff here. He was needing to go a distance of that many meters. I'm just going to convert it in my head. We have an acceleration. We have a time. And we want to know his initial velocity as he opened the parachute. So what information do we now have this time? Sorry, I mean, we're looking for initial velocity is what I'm going for. So what of the 4 variables is the 5th one that we have nothing for final velocity, right? So we need to pick out which of these formulas here does not involve a final velocity anywhere. And that would be this one here. Does that make sense? We're still looking for the unknown of the initial velocity right there. But first you got to figure out which of the formulas to use. So the advice I would give, identify which 4 variables you have. Identify which one you don't care about, and then use that to narrow down which one you're looking for. So this time our formula is d equals vit plus 1/2 at squared. And we need to solve for vi. So let's plug in some values. 1530 equals vi times 25.7 seconds. Seconds below. Plus 1/2 of negative 6.3, 25.7 seconds squared. Units in there. I'm okay if from here you go right to the answer. If you can handle the algebra, I don't need you to show me all the steps. But please give me the formula. Give me the first step where you actually plug some numbers on the paper. That way at least I can look at something in case you screw up. But as of this point here, if you know how to do the algebra, which would be what? Take all these numbers, put them together, add them to the far side, because really this negative is making the whole thing negative, so add them across, and then divide by 25.7. So long as you can handle the math, you can just go right to tell me what your initial velocity was. Let me know if I need to get an answer.
Negative 1.34. I got 104. I got negative 42. I got negative 21.
Okay. Right off the bat, it should not have been possible for you to get a negative. Here's the rationale why. Let's make sure you did the algebra right. all of this stuff right here is a negative number, correct? Right? Because the positive times the negative times the positive. All of this, whatever this stuff right here is, this should be a negative value. With me there? To get it to the other side of the equation, you should have then added that negative number across over here, meaning that this number right here from 1530 should have gotten larger. And then when you divided it by 25.7, it should still be a positive number. So right off the bat, if you had a negative number, you must have made an algebra mistake somewhere. Does that make sense? I'm guessing that if you got the negative number, you subtracted. Yeah. What did you guys get otherwise? 140? Cool. So long as that's the consensus.
Should you like put it over to the other side in order, or does it matter?
Well, here's what I do. I would calculate what all of this happens to be right here as a number, right? So negative something really big, right? And then I would take 1530 and I would add that number to it.
Oh, it's going to be
Right? Because all of this is a negative number. So calculate a really large negative number. Let's call it negative 1,000. I know it's not, right? Then add 1,000 to both sides. Take your 1530, add 1,000, and then divide up to 25.7.
Do you put the 25 in there?
Did you square that?
Yeah.
And then you multiplied by that,
Yeah.
and then I multiplied by 0.5.
Okay.
Did it ask for a velocity or a speed velocity? We're not done then. Don't forget the details. First I had to get my sig digs right. 140 meters per second is 1.4 times 10 to the 2. And since it was a velocity, I'm going to put a capital D afterwards because he was probably going down. See how it would be anything otherwise.
Oh yeah, I didn't see it.
You good? Quick thought here. You know how when you have to do like partial calculations in between, do not round that number. Whatever you got for like this number right here, make sure you use all of the digits. Do not skip on digits. The most common way you're going to screw something up and you'll go, oh my goodness, in physics, is that you decide to not hold your precision until the very end. Do not round until you are done the entire equation. Because if you just keep rounding little by little by little, then you're off. Anybody have issues with that one still? Okay. Alright, let's try another one. A bullet accelerates the length of the barrel of a gun 75 centimeters with a magnitude of that acceleration. What speed does the bullet, that's not bullet, exit the barrel? Okay, the first thing you might notice as you see the question here is I only see two numbers. Shouldn't I have three? Start writing them up. We have a distance of 75 centimeters. Can you guys convert that to meters in your heads?
Yeah.
What do you need to do to get centimeters back to meters? Times 10 to the negative 2. Essentially, you need to move the decimal place back twice. So it's 0.75 meters. So there's our distance. We have an acceleration value of 535 times 10 to the 5. That's incredibly fast acceleration. But that's all it seems like it has. But wait. What was the initial speed of the bullet?
0.
Yeah, like before you shoot the gun, the bullet's not moving, right? So your velocity initial, it's hidden, but it was actually not moving when we started. There is another piece of information there. And we are looking for our final velocity. Okay, so the thing we know nothing about is time, which is fine. We only ever need to have to work with 4 out of 5, so go back and find a formula that does not involve time. This is starting to get a little busy here. Can you guys figure out which formula we need? This one here. Yeah, the last one. So we haven't used this one before, but I don't know that I need to add much context. I mean, at some point, here's just a new formula, right? So do your algebra. Sorry, that is a plus sign there. Okay, so we need velocity final squared equals velocity initial squared plus 2AD. So 2AD. Okay, velocity final, we don't know. So what we want. Velocity initial is nothing. This actually is pretty straightforward, isn't it? Take 2 times by 5.35 times 10 to the 5. And times by 0.75. By the way, this is velocity final squared. Don't forget to square root. That'd be a bad thing to do. 2 times 535 times 10 to the 5 times by your 0.75. But that's velocity final squared, so square root it when you're done. Consensus? 895? What'd you say?
895, but
895?
sig digs, because we have 0, is that?
Okay, so 0 is a whole number. It has an infinite number of sig digs. It is 0.00000 for forever. Does that make sense? So it's an exception. If I asked you how many sig digs 12 eggs was, there's an infinite number there, because you can't have 12.1 eggs, or, you know what I mean? So the number 0 is kind of similar to that. It's exactly 0. So don't let the 0 limit your sig digs. We still only get 2 though, don't we? Yeah. So 9.0 times 10 to the 2 meters per second. We wanted a speed, so we're good to go. That's a 9, by the way. You guys get that too? So far, so good? Okay, here's a chart that just kind of goes through what I've been trying to hint at here. You've got these 5 formulas. All of them are missing one of the 5 variables. So if you know nothing about distance and you're not trying to solve for it, use this one. So anyways, some people in the past have taken this chart, they've cut it out, and they've put it on their formula sheet. If that works for you, feel free. I think at some point though, you'll get pretty good at recognizing which one to use. So, okay, let's throw some twists in now. So now that we're getting pretty good at just plugging in some regular formulas, one of the things that I might do is make you work with different unit types. So here's a scenario here. Studies have determined that the average wet and dry surface deceleration for brakes on a Camry are 24.2 feet per second squared. Feet. We have to convert. And 23.3 feet per second squared. So you're actually able to decelerate better on the wet surface. I think I must have put them in the wrong order. It must be this one for the wet one and this one for the dry. It's gotta be it, right? Yeah. It's gotta be. I must have put them in the wrong order. Okay, but you guys see the twist here though, right? We're gonna have to convert feet per second. Hence the next phrasing here, there are 0.3048 meters in 1 foot. Here's another thing though. I give you more information in kilometers per hour. Also not the right type of units. We want to figure out the difference in stopping distance between the two conditions if you had 2.3 seconds in a collision. This just took this to the next level, eh? Because it's not just about plugging some numbers in a formula and getting your answer. We're going to have to do a bunch of unit conversions. We're going to have to do this work twice and then figure out how much better the dry deceleration value is than the wet deceleration value. So, okay, let's start it. 100 kilometers per hour. Let's start with that. That's not useful, is it? I think I've taught all of you at some point, except maybe we'll work on this. Maybe we did this when we were in physics lab. How to convert units by unit, like looking at fractions and canceling unit types. For example, let me redo this though. That's messy. If I give you 100 kilometers in an hour, I don't really want to use the unit kilometers. What unit do I want to use? Usually it's meters, right? So what I'm going to do is I'm going to put a meter on top and a kilometer on the bottom. And what you'll see is that the kilometers will cancel. We're doing this at some point? Yeah, it's basically stoic, yeah. So then how many meters are in a kilometer? There are 1,000 meters in 1 kilometer. Okay, but now I've got this hours unit. I don't want hours. What's the typical unit we use instead? Seconds, yeah. Okay, so if I want to get rid of the hour symbol though, see how the hours one is on the bottom of the fraction? So I'm gonna have to put another hours one on top and put seconds on the bottom to cancel those out. Okay. So this kilometers here cancel with that one there. This hours here cancel with that one there. And now the units that are left are ones I can work with. Meters over seconds. How many hours is, what's the ratio between hours and seconds? 3,600, yeah, because there's 60 seconds in a minute times by 60 minutes in an hour. So there are 3,600 seconds in 1 hour. We did a little bit of this last year, right?
Never seen this before, but
I haven't shown you this? We didn't do unit counseling?
this was our physics in class.
Okay.
This is all.
Okay, well, I'm glad does this make sense though? As a way of counseling? Or do I need to slow down here? Okay. You guys who took chemistry, this is good, right? Okay. But you guys, okay. Let me just do a quick aside here, just to make sure everyone's on the same page. Let's say that I gave you worked for 15 hours, and you made $10 in 1 hour. Can you visually see how the hours symbols kind of cancels each other? Well, 15 times 10 would be 150. The unit that would be left would be the dollar sign. So if you worked 15 hours at $10 an hour, you'd make 150 bucks. That kind of makes logical sense, right? But like here's a way to visualize it with the units. If it's on the top and bottom of a fraction, you can cancel it. But I can actually change the way this works here. What if I had a goal to earn $200? What if I needed to earn $200? And I earned $10 in 1 hour? Well, according to this, I would need to work for 2,000 because 200 times 10 is 2,000. That makes no sense, right? I'm not working for 2,000 hours to make 200 bucks. So what I need to do on this one here is I need to kind of flip the way this fraction works. Rather than writing the 10 on the top and the 1 hour on the bottom, what I'm going to do is I'm going to put the 1 hour on the top, and I'll put the $10 on the bottom. You can see how this money unit will cancel with this money unit. What unit's left? Hours. If you work for if you want to earn $200, and in 1 hour you make $10, 200 divided by 10 would be 20. It's not working yet. 20 hours, because hours is the units that's left. That makes sense? I'll do more examples. So let me go back up to the one we were working on then. We had 100 kilometers an hour. I don't want kilometers, so I'm going to put it on the bottom of the fraction. What I do want is meters, so I'll put it on top. This kilometers on the top can cancel with this kilometer on the bottom. How many meters are there in a kilometer? Well, there's 1,000 meters in a kilometer. Why, just erase this, why shouldn't I go with 3,600 seconds in an hour like that? Why does that not help us get rid of the math orientation? Well, it's this hour symbol right here we want to cancel. See how it's on the bottom of the fraction? If I put this other hour symbol on this bottom of this fraction here, it's not going to cancel, right? But if I flip my fraction upside down, this ratio, and I put the hour symbol on top and seconds on the bottom, really what I need to do is I need to take 100, I need to times by 1,000. You could divide by 1 if you wanted to, but there's no point in that. And you could times by 1 and divide by 3,600. I know I showed you guys this because we did this in chemistry before. If I had 100 grams, you would times by a mole for every 40.08 grams. Remember doing something like this in chemistry? We did it in chem unit. If I gave you 1.3 moles of something, you would times by 40.08 grams per mole, and you'd cancel the moles units. Does that ring a bell?
I did that in that part.
It was like the very, very last part of count. Okay. Well, anyways. Okay, I'll work with units a little bit more later if you guys need. Someone help me out here. What's 100 times 1,000 divided by 3,600? 27?
Yeah.
Okay, thank you. Okay, so we have our first value here. our initial velocity is 27.7 repeating, but now I finally, after quite a sidebar here, I finally have a unit that I can work with, meters per second. Okay, I also have some other units here that are no good. I've got 24.2 feet per second squared, but that's also not a unit I normally work with. So the unit that I don't want is the unit of feet. So in this fraction right here, I'm going to put feet on the bottom of the fraction, because hopefully you can see that the feet sign right here will cancel. What unit do I want? Meters. So I'll put the meters symbol on the top. Look at how my units will work now. When I'm done, it will be meters over seconds squared. Well, now I just need to throw my my units in. It says right here there are 0.3048 meters in 1 foot. So right here I would write in 0.3048. There are that many meters in 1 foot. Can you visualize here how this feet symbol cancels that feet symbol? The unit that'll be left is meters over seconds squared. And what I have to do mathematically is take 24.2 times by that 0.3048 number. And if you want to, you can divide by 1, but you don't have to divide by 1.
Mr. Cleaver, can you please call 3500? Mr. Cleaver, please call 3500.
Anybody get an answer?
7.376.
And that number probably keeps going, right?
A little bit.
Okay. So just give me the first two numbers. 7 point what?
37.
Good. I'll call it 7.3 dot dot dot. This is what I'll do as my convention. I'll just write 7.3, and even though I know it technically should have rounded up there, I'm not rounding this number. I'm making sure that that 7.376, whatever the numbers are there, I'm using all of them, right? So that would be my acceleration. I'm going to go with a negative acceleration. Shouldn't it be negative? We're slowing down, right? And which one was that? That one was the 24.2. So that one would be how fast you can decelerate on a dry surface. I have to do the exact same thing and find out how fast you can decelerate on the wet surface too, though, right? Won't the math be the same, though? You'll take whatever the number is, so this time 23.3, and you'll times by 0.048. Find out how fast you accelerate on the wet surface, or decelerate on the wet surface. Just give me the first two digits.
2.1.
Okay. And again, there's a lot of digits afterwards, so I'll just put some decimals in. So the twist of this question so far has been we need to convert our units out of these different unit types, right? Okay, other things I know. So I have two different types of acceleration, hence we're going to do the equations twice. I also know time, though. Time is 2.3 seconds. And there's one more thing I do know. I'm going to pick out what it is. There's no more numbers left, but there is one still there. It's implied. What did you say? Yeah, after what though? Final velocity, yeah. Yeah, our final velocity is going to be 0, right? Because we are stopping, aren't we? We got that right? We have an initial velocity. We have time. Oh. Yeah, velocity final is 0. We know how fast we're going to decelerate. I just realized something here. I shouldn't have used the phrase stopping distance here. Because in 2.3 seconds, you might not actually come to a complete stop. I just realized that. I think I was kind of leading you wrong there. Can I say that one more time here? I know I used the phrase stopping distance in my example here, but I'm not sure that's fair. Because I don't think that in 2.3 seconds, I can guarantee that you actually came to a complete stop, especially in the wet conditions. Does that make sense? So I don't think we actually know velocity final is 0. Normally though, if I use the phrase stopping distance, it means you come to a complete stop. You get what I'm saying here? Okay, let's try some math now. We got to do this twice. Once I have to run the numbers with the wet acceleration. Once I have to run the numbers with the dry acceleration. Because I'm looking for the distance it takes. So I need a formula that has a velocity initial, a time, a distance, and an acceleration. So that's d equals VIT plus 1/2 AT squared. Why don't I color code this, just for me here? I'll do the dry one in purple ink, and then later I'll do the wet one in black ink, just so we can keep them separate. We finally have all sorts of values we can work with. Let's plug them in. So let's do purple first. Either way, we still don't know our distance. That's what we're trying to figure out. What's our stopping distance? Our velocity initial is 27.7 repeated meters per second. Make sure you use the 27.7 repeated. Our time was 2.3. Our acceleration under dry conditions is a little bit better. It's negative 7.3, but don't forget, use that whole number. Don't just round it there. Use whatever that 7.3 was there. And then we need the 2.3 seconds squared. If you had 2.3 seconds to stop, how far would your car skid in that 2.3 seconds? Because I'm not actually sure you'll actually come to a complete stop. We're just wondering, how far would you get? Like, you might still rear end the car in front of you. Anybody get a value?
I got 167. I got 100. I got 40.
Okay.
I got 45.
Let me grab my calculator.
I got 43. That's new though.
Okay. I need to make a value here. It was 24.2 divided by or times by 0.3048. Okay, I'm just gonna store that number right there as A in my calculator, just so that I can use it later. Okay, so here's what I would have done. I would have taken 27.7 repeating. That should be sufficient. Times by 2.3 plus, I'll go with 0.5 as 1/2. That's your guys' class, isn't it? Sorry, I forget that we have a 5-minute overlap. We'll stop after this example. Watch the very end of my YouTube video if you can, okay? Sorry guys, I forgot. We need that number, so negative that A value. And then we need 2.3 squared.
Does the last number need to be in brackets or do we leave it out of brackets? Because that's what
The 2.3 squared?
Yeah.
Yeah, you probably don't need the brackets. I'm just being...
So I got two different numbers when I put it with brackets and without.
Okay, then do it with brackets then. Okay, here's what I got, 44.37. That's it? Okay. I gotta speed up here, we're running out of time. Sorry guys over there, I apologize. Alright, so that's, probably 44 meters with our sig digs. So, just for a little context here, if you're using under dry conditions, it would take you 44 meters of stopping distance. I mean, you're not actually maybe coming to a complete stop, but in the 2.3 seconds, that's how far your vehicle is going to skid as you're hitting the brakes. Does that make sense? The second time we do this, the only change, hopefully you guys see here, is that we have to change out that acceleration value. So let me do that one in black now. You still use your 27.7. You still use your 2.3 seconds. Now this number is the negative 7.1 number and 2.3 seconds squared. Sorry, I'm running out of room. Okay, first I need to find that value. If any of you have like those calculators, you can go back up to find numbers. You're gonna like this in physics because often you have to go back and like find an exact value that you've used before. If not, get in the habit of storing them as you do them. So like when we did, what was it, 23.3 times by 0.3048, I'm going to store that number as B, so I can use the B number in the future. Okay, so this should have been 27.7 repeated, that should be sufficient. Still times by 2.3, still adding a half. Don't miss that negative sign because it's slowing down, right? So for me, I'm using B and then 2.3 squared. This time I got 45 meters. But doesn't that make logical sense? Under the worst conditions, you're going to skid just a little bit further than you did under optimal conditions, right? So under dry conditions, you're going to need 44 meters to get yourself slowed down. Under wet conditions, you're actually going to skid an extra meter. So last thing we should do then is this was like 45 meters. The question actually says, what's the difference in stopping distance? So now we need to subtract those. So 45 meters minus 44 meters means you need 1 meter extra, I guess. One more thought, sig digs. We only have one now, right? But here's the reasoning why though. What did we just do with these numbers of 45 and 44? We subtracted them, and the rules for subtraction are you just line it up based on precision. So even though we lose a sig dig now, that would be proper. So because you line it up and say 45 minus 44 as you subtracted. I guess there were other numbers there, 45.104. Well, no, because these should have been rounded to 2 decimal places each. So it would make sense to maybe make it 1 meter. Yeah, that was quite an example, wasn't it? Do I have more? Oh, I still have more. Oh, I had one on this. Okay. I spent a lot of time at the beginning of class talking about stuff, that's why. Did that last one make sense?
Yeah.
Okay. The big challenge, I think, for some of you is going to be just the unit conversions. So if you can think of like the unit that you have, you want to cancel it on the bottom. The unit you want goes on the top of the other fraction. Once you get the hang of that, it's actually not so bad. So why don't we start tomorrow's class then with the example with the Z22, and then we'll hop right into graphing. So we'll try to be ready to go right off the bat. Okay. So we're gonna have a smoke off. Who's not here for? And Darius. Okay, well, I'll make a video like I always do. So we'll chat another day. Okay, thanks guys.